So now let's look at another advantage of using our negative feedback amplifiers. So when we use our negative feedback amplifiers, we've said that in some specific cases that can lead to an improved signal-to-noise ratio. And so what we're going to see here, by considering 4 different simple block diagrams, is that this negative feedback has the ability to improve signal-to-noise ratio. So as I have underlined here, it can improve the signal-to-noise ratio. It's not going to, but it can. And in order for it to even be possible, the noise has to be generated in the amplifier. If, on the other hand, our noise is part of the input, then our negative feedback cannot improve the signal-to-noise ratio. So in that case, we just can't help it by having feedback in our system. And we'll see that played out in our 4 different circuit or our 4 different block diagrams we're going to look at. So before we get into looking at those block diagrams, let me define a couple things related to our signal-to-noise ratio so that we're all on the same page for this simple analysis. So we can define the signal-to-noise ratio of our input as the signal in divided by our noise in. And so this could be talking about any number of signals. Maybe we have currents, voltages, anything like that. To keep things simple, let's maybe just assume these are voltages. So our signal in might be some input voltage Vi, and our noise in might be some noise voltage V sub in. Now what we're going to use and we're going to focus on a little more is our output signal-to-noise ratio. And so this we can say is our signal at the output and our noise at the output. And so this is equal to whatever gain ATI is being multiplied by our signal. So we have some signal gain multiplied by our signal. And then we have some ATN, which is some noise gain that's multiplied by our noise, that's input. And so I think that's pretty straightforward, but again, just so we're all on the same page. So let's go ahead and look at our first configuration. So of course here we do not have any feedback, so let's go ahead and calculate our output signal-to-noise ratio. So we have our output is V output A, and so we can see that this is going to be partly due to this input voltage over here on the right, and partly due to this noise voltage, which is coming in between our 2 amplifiers. So we have our input signal, which is being multiplied by both gains, A1 and A2, and then we have our noise signal, which is just being multiplied by our A2 gain. So we get, if we plug in the values for these gains, is we have 100 Vi plus 10 Vn. So now if we're looking at our signal-to-noise ratio of our output, we have our output signal divided by our noise in the output. And so that is going to be our 100 times Vi, that is our signal, and then 10 Vn is our noise component. So our signal-to-noise ratio is then 10 times our input signal divided by our noise input. So we have 10 Si. Okay. And so ideally we want this number to be higher because that indicates that our signal is much stronger than our noise. So 10, not too bad. So let's move on to our second case, where the only thing we're going to adjust is now we've moved our noise over such that it is being added to our input before it even goes through our amplifiers. So what we can say now is that our V output B is equal to, so we have A1 and A2 being multiplied by Vi, but now we also have A1 and A2 being multiplied by our noise voltage Vn. So plugging in the values for gains, we have 100 Vi plus 100 Vn. So again, we can calculate this signal-to-noise ratio of our output. That's our output signal and our output noise. And in this case, our output signal is the 100 times Vi. Our output noise is the 100 Vn. And so we see that's just equal to our signal in divided by our noise in. And so in this case, we can see it's actually worse to have that noise as part of the input. And of course, the only reason for that is because in case 2, our noise is going through more of the amplifiers than it was in case 1. So in case 1, it was only going through this second amplifier A2. Okay, so that both of those cases were without any feedback. So now let's see how we can improve on this if we incorporate some feedback. So in this case, we have 2 sort of forward amplifiers, our A1 and our A2. And then we have this feedback path with beta equals 0.01, and we see our noise in this case is being introduced in between A1 and A2. Okay, so let's analyze this. So we have our V output C, which is equal to, so now we have A1, A2 times this air voltage, V epsilon, plus A2 times our noise voltage, Vn. Well, we can break this down a little further and we can describe what our V epsilon is. So we can say our V epsilon is equal to our V input minus our feedback voltage, VFB. Well, our VFB is just equal to beta times our VOC. So now what we can do is we can take this V epsilon and substitute it into our previous equation. And what we're going to get is that our V output C is equal to A1, A2 times VI minus beta VOC plus A2 times Vn. So what we can do with this equation now is we can solve for our VOC. And if we do that, what we'll get is that our VOC is equal to A1 times A2 divided by 1 plus beta A1 A2, all of that being multiplied by VI, so that's our signal that's being input on the far left of our block diagram. And then we also have a second term, which is A2 divided by 1 plus beta A1 A2, all of that multiplied by our noise. And so if we plug in values of A1, A2, and beta, so A1 is 10 to the third, A2 is 10, beta is 0.01, what we get is approximately 99.010 VI plus 0.099 Vn. So we go to calculate our signal to noise ratio of our output, and that's going to be our output signal divided by our output noise. And we get that that is approximately the 99.010 VI divided by our 0.099 Vn, and this is equal to 1000 SI divided by Ni. So now we have a signal to noise ratio of 1000. So a vast improvement over the previous two configurations where we didn't have feedback. So a couple things I want to point out though. So maybe in this situation, this is some high power amplifier. And so typically our high power amplifiers are going to have more noise introduced. So sort of we would block these two together. And then this would be a lower power, a low noise preamplifier. So low noise preamplifier, or often just preamp for short. And so this is a pretty common configuration, particularly when you're dealing with small voltage signals and you're trying to sort of protect them from having any noise introduced. Okay, so if you are paying close attention, you might say, well, how is that any different than if we just went to case 1 and we just changed this first value here and we said, well, instead of 10, let's just make this 10 to the third as well. So then we would also have 1000 signal to noise ratio. And so the reason that that doesn't work is notice that our input signal would then be multiplied by 10 to the fourth, and our noise signal would be multiplied by 10. And so if we think about sort of how saturation works for op amps, if our output signal tries to get too high, it can only go up to a certain limit depending on the power sources that are powering the amplifier. And so the same is true here, regardless of what amplifier we're using, we're going to have sort of some upper and lower limit. So we could call, for instance, V plus and V minus. And so, of course, for a typical circuit, 10 to the fourth is going to be well above this upper limit for our V plus. However, if we have that V plus and V minus, granted this 99 VI, that might still be pretty high, but that's going to be much more likely to be within that limit than, for instance, your 10 to the fourth. So that's sort of the difference between case 1 and case 3. So the last case we want to consider, case 4, is essentially the same as case 3, except now our noise is coming in over here directly with our input. And so what we can do in this case is we can actually just use our previous equation. We can sort of combine our A1 and A2 into a single gain. So we can say our V output D is equal to, and so remember our old equation we had A divided by 1 plus beta A. Well, now our A is A1 times A2. So we have A1 times A2 divided by 1 plus beta times A1, A2. And instead of just having a single input voltage, we now have the input voltage is VI plus Vn. So if we calculate that, if we plug in these values, 10 to the third for A1, 10 for A2, and 0.01 for beta, we get that our VI is approximately, or this VOD is approximately 99.010 times VI plus Vn. So both VI and Vn are multiplied by the same value. And so of course what that means, if we go to calculate our signal to noise ratio for the output, we see that's our output signal divided by the noise in our output, which is approximately 99.010 VI divided by 99.010 Vn, which equals the signal to noise ratio of just 1. And so again, the point of that is just to emphasize that the feedback, the negative feedback, has the ability to help improve our signal to noise ratio. But if our noise is part of the input, then our negative feedback is not going to be any help.